Greetings and welcome back. This is section 18, antennas. And this is actually one of my favorite ones. And let's see, antennas. Now with antennas, you don't necessarily have to go out and buy expensive antennas commercially made. You can make your own. I've made a lot of antennas and they've worked very, very well, even some better than the commercial ones. So this is a simple dipole that we have here. It's made from 2 pieces of wire and some coax cable. Simple dipole mounted is so the conductor is parallel to the Earth's surface. It's horizontally polarized antenna. So if it's flat to the Earth's surface, it's horizontally polarized. And a couple of notes about the wire. I usually use 12 gauge stranded, just regular house wire. I have the coax connected. One side goes to the center, the other side goes to the shield, and I wrap well, if it's RG58, I wrap a half dozen loops as a choke. So we're going to get into chokes a little bit later, but that's all it is. And then you have a PL259 on the other end connected to the radio, and you're set. Now this has to be a specific length for whatever wavelength you're on. This is a single band antenna that you have here. The direction of radiation is the strongest from a half-wave dipole antenna in free space is broadside to the antenna. So the way it is right now, looking at it, you're getting the maximum radiation towards you and away from you. So if this was north, this was south, your radiation would be east-west. If this was east, this was west, your radiation would be north-south. So it's on the broad side of the antenna, your maximum radiation. So they're directional, somewhat. The approximate length of a 6-meter half-wave wire antenna is 112.3 inches. So this goes back to that wavelength calculation we did a few slides ago. Frequency in megahertz over 300, and that'll give you the approximate electrical wavelength. Now, if you do have this, I usually do mine by eye with just a tape measure and measure it out. But if you have a antenna tuner or something that measures SWR, you can actually tune this right to the frequency that you're operating, your desired frequency. So this one happens to be 14 gauge wire. I like to use 12 because it's just physically stronger. But you can use 14, you can use 18. I've seen 18 gauge for campground antennas. If you like to camp a lot, you can use some lighter gauge. But I typically use 12 gauge just for the strength. And they have a ball end in here, balanced to unbalanced. I'm going to turn down the radio here. And typically this is what's called balanced coax. It's 50 ohms. To unbalanced. This is an unbalanced line. To change dipole antennas to make it resonant on a higher frequency, shorten it. So if I have a 17-meter antenna, I can make a 10-meter antenna really easy out of it. Just shorten it. Regarding vertical antennas, the electrical field is perpendicular to the Earth, 90 degrees. So this is horizontal polarization. This is vertical polarization. So when you get up to the higher frequencies, I would say 17 meters on up, you can use vertical polarization. It's possible to string up an antenna very easily with vertical. If you're going for a longer wavelength like 80 or 160, you got probably be horizontal unless you have a very, very, very large tower. And there are some advantages and disadvantages to each antenna system. Alright, so here's the vertically polarized antenna. The magnetic field is going in that direction. You have 2 fields, the electric field and the magnetic field. The electric field is this direction, and the magnetic field is this direction. This is what we call the right-hand rule, and these are the eddy currents going through. Alright, same with this. This is horizontal. You can see the magnetic field. You can see the electric field. Okay, the approximate length in inches of a quarter wavelength antenna for 146 megahertz is 19 inches. And this was one of my first antennas that I built. You can get some coat hanger and an SO239. You used to be able to get these at Radio Shack. I don't think they carry them anymore, but this is an SO239 chassis female. And you just solder on bits of coat hanger. So if you got a piece of coat hanger, 19 inches, here's 19 inches, and you have 4 radials for ground, 19 inches. So you can put one per corner on here, and your center radiator up top, and the ones on the bottom are going to be your ground plane. And this antenna works really, really well. I have had one for years up on the roof. It takes a lot of punishment. And if it gets bent, you just rebend it back. I mean, you know, it's very easy. It's a nice, rugged, simple antenna. The quad Yagi dish antennas are directional antennas. So here's some directional antennas, and I've built all of these. And there's certain advantages to each one. But these are directional antennas, so they go in one direction. They concentrate in one direction. The beam antenna concentrates signals in one direction. So here is your Yagi beam, and you can see Yagi beam versus dish. So here's the Yagi beam, and it's kind of like a fishbone or a wide lobe or beam, and a dish is a lot more narrow. And let me go back. And depending on how many elements you have in your beam will determine how narrow this guy can get. And I've seen 13 to 15 element beams, and this thing gets really narrow, really directional. There is a certain point that you don't want to go over certain elements because there's no advantage to it. But that's later on in the general and extra portion of the license test. You guys don't have to know anything about that right now. Directional antenna would be useful for hidden transmitter hunt. So fox hunts. A lot of amateur operators, they like to do this as a sport. It's called a radio sport, and it's fox hunting. So they have a hidden transmitter somewhere, and you have to find it, and you find it with a directional antenna. If anyone was in the Civil Air Patrol, they do the same thing with EPIRBs and ELTs for aircraft and boats. When there's an emergency signal being transmitted on 121.5, or an EPIRB on a boat, 121.5, same frequency, and they do the same thing. They kind of find the transmitter, because that transmitter can block real emergencies. So I did that for a very, very long time in the Civil Air Patrol, and it was a lot of fun trying to find these ELTs and EPIRBs. But the ham radio community does it for fun. So that was the difference between the fox hunting and hunting for ELTs. To locate sources of noise, interference, or jamming, use radio direction finding equipment. So here is a handheld Yagi. So you can build your own. I've built my own out of tape measure. I've seen commercial ones available from Arrow Antenna. They're actually made from arrows, aluminum arrows. And it's really useful to have just a handheld directional antenna if you want to do fox hunting or direction finding. Okay, to increase the signal strength in a specified direction when compared to a reference antenna is referred to the gain of the antenna. So if I go back a few slides to that 19-inch antenna on the SO239, that is a gain of 1. So other antennas are compared to that style of antenna with that gain of 1. Okay, so here's a regular isotropic antenna, just like I just showed you, with an omnidirectional path, and that one had typically of a gain of about 1. Now here is a beam antenna to compare it, and you can see the lobe going out, and this is your maximum signal strength is in this area. So this is very directional. This is like for a beam antenna, and this is modeled in 3D space. over here. And there's software you can do for modeling for that. Horizontal antenna polarization is normally used for long-distance weak signal CW and single sideband contacts using the VHF and UHF band. So this is on the lower portion of the 2 meter and 440 megahertz band. We have single sideband. So typically they're horizontally polarized on single sideband. Signals could be significantly weaker if the antennas are at opposite ends of the VHF or UHF line of sight radio link is not using the same polarization. So if you have one, let's say you have a HT radio, a handheld transmitter, you have one vertically and you have one horizontal. It's not going to be the maximum efficiency, so your distance is not going to be that great. But if you have them in both aligned in the same direction, like vertical, both antennas are vertical, you're going to have maximum efficiency. A properly mounted 5/8 wavelength antenna for VHF, UHF mobile surface offers a lower angle of radiation and more gain than a quarter wavelength antenna, and usually provides improved coverage. So that little antenna that I showed you with the 19 inches, that's considered a quarter wavelength antenna. Now you can make the antenna longer by different wavelengths. You got to be at the wavelength you're operating at, or the antenna is not going to resonate. So you can't go out there and just have a random length of antenna and expect a great efficiency. You got to have it cut at usually quarter, half, 3/4, 5/8 wavelength. Any one of those are pretty efficient wavelengths to cut antennas at. So 5/8 is really popular for 2 meters, just for example. It's not too terribly long. VHF and UHF mobile antennas are often mounted in the center of the vehicle roof, which normally provides the most uniform radiation pattern. So that's the best area to mount your antennas, is right directly in the center, right on the roof. I have mine on 2 meters, and it works very, very well. I got good quality coax feeding into the what's called an NMO mount, which is requires a 3/4 inch hole through the roof. I got it right directly smack in the middle, and it works really well. Compared to a mag mount on the trunk, you got a lot of sheet metal you got to contend with in your front radiation pattern, and it's going to affect you a little bit. A type of loading when referring to antennas is when the inductor is inserted in the radiation portion of the antenna, making it electrically longer, is called a loading coil. So you'll see this on cell phone antennas, the old cell phone antennas too. They'll have a coil in the middle of the antenna, and that's a loading coil. Now it makes the antenna look electrically longer, but not physically longer. And that's the end of that section. We're going to go on to the Q&A sections next. See you then.